Alright, for our lesson for day 8, we're going to build on what we learned about direction, angles, and magnitude, and actually go the opposite direction and even use that to solve problems. So far we've been looking at cases where we knew the components and we figured out the magnitude and direction from that. But now we're going to go the opposite way, where we know the magnitude and direction and we figure out the components. And if you think about it, this is actually probably closer to real life in most aspects, as you'll see through some of the word problems that we're going to do. Okay, so we have this formula here. Our vector v equals the magnitude of v times cosine x times I plus sine x times j. Now notice in this case, x is the angle, the direction angle of the vector. Now it's important that we remember our terms here. Remember that direction angle is an angle in standard position. Alright, so just like the angles on our unit circle, it starts at the positive x-axis and rotates counterclockwise. Alright, now, you might say, well, where does the cosine x and the sine x come from? Well, that is directly related to our unit circle. Remember, all the points on the unit circle were cosine, sine. Cosine, the x-coordinate, a horizontal measure. Sine was our vertical, our y-coordinate, and the vertical measure. Alright, so you'll notice here we have the I and j unit vectors. So really what we've done here, if you guys remember what we did in our previous lesson, where we found the unit vector and then we forced it to have the magnitude we wanted, alright, this right here is the unit vector in the direction that we want. And then we multiply it by the magnitude that we want, and that gives us a vector going in the direction that we want with the given magnitude. Alright, so let's look at an example right here. It says find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles an hour at an angle of 30 degrees below the horizontal. Now notice, and this is going to happen a lot, notice the angle that we're given initially is not the direction angle that we need in order to make our vector. Okay? 30 degrees below the horizontal, evidently this plane is flying towards the west, okay, and it's going down at a rate of 30 degrees. Alright, so that 30-degree angle is right here, but that is not the angle we're going to use to form our vector. We need the direction angle, which is this 210-degree angle in standard position. Alright, so the vector of our airplane, we'll call this A for airplane, is going to equal the magnitude that we want, 100 miles per hour, times, and you can write this in IJ notation, or you can write it in component form notation. I'll do it in IJ initially here. It's the cosine of 120 degrees times vector I plus the sine of 120 degrees times vector j. Okay? Now, at this point, it's just a matter of doing the trig. We have vector A is 100 times cosine of 120, that has a reference angle of 30 degrees, so cosine is root 3 over 2. So we have root 3 over 2I plus sine of 120, sorry, that's a negative root 3 over 2 because it's third quadrant. So plus a negative 1/2 j, because the sine of 120 is negative 1/2. So now we multiply in the 100, and we get vector A to be negative 50 root 3 I minus 50 j. Okay? Again, that's an IJ unit vector notation. We could write it in component form as well. which would be negative 50 root 3, negative 50. Okay? So that's how our airplane is traveling. Now, it's also important to understand what this means. This means that we are descending at a rate of 50 miles an hour. So if we're looking at just the vertical movement, it's going down at 50 miles an hour. All right? In other words, when it hits the ground, if it hits the ground at this angle, it's going to hit with enough force, with the same amount of force as if it were just going straight down at 50 miles an hour. That's a lot of force. Okay? Also, while it's descending, this horizontal, 50 times root 3, which is about 1.7, that would be about 85 miles per hour going towards the west here. All right? If we're so far away from the airport that we're covering 85 miles of ground for every hour that it's in the air, that tells us a little bit about the horizontal movement. Okay? So that's how we would find our vector. Now, a couple of things that we haven't dealt with as much. Velocity and movement really make sense. Force is sometimes a little bit hard to grasp. Okay? But we really have to think about, especially in this case, gravity. And what's happening with gravity, and what does it mean when we say something weighs something. Alright, so here we have this boat that's on this ramp, and the ramp, you'll notice the ramp here is at a 15-degree angle from the horizontal. Alright, so right here is 15 degrees. Okay, now, there's a couple of different things when we're dealing with forces. Alright, this right here, BC, is the force that the boat and trailer are actually exerting on the surface of the ramp itself. And that's why you'll see here this is labeled perpendicular. Okay? That is not how much it weighs. If you think about it, okay, what something weighs is impacted by gravity. Alright? Gravity pushes straight down on an object. So this vector right here represents the weight of the boat and trailer. Alright? So that actually, the magnitude of that is actually what we're looking for in order to find the weight of the boat and trailer. Okay? Now, you have this little vector down here as well, AC. And AC, notice, is parallel to the ramp. Okay? And the reason why that's parallel to the ramp, for one, it makes it perpendicular with this vector BC. But more importantly, this 600 pounds is required to pull the boat and trailer up the ramp. So that vector right there is equivalent to vector AC right here. Okay? So that actually tells us something. The magnitude of AC equals 600 pounds. Okay? There's 600 pounds of force pulling that boat up. Okay? So now we need to use a little bit of geometry, and I want to zoom in a little bit here so that we can see it even better. Alright, you'll notice we have the horizontal here, we had the 15 degrees over here, which means this angle right up here is going to be 75 degrees. Okay, we have a right triangle. Now, we also have a right triangle right here over by B. Okay, well, if this is 90 degrees and this is 75 degrees, this little angle right here has to complete the full 180. Alright, that's why they've labeled it 15 degrees. Okay, so you have to think through the algebra a little bit here, but that right there is 15 degrees. And at this point, guys, really all we're doing is a little bit of right triangle trig. we have a right triangle, and we know AC. We are trying to find the hypotenuse, okay? And since this is the boat, I'm going to call this vector B. All right, vector B. So the magnitude of vector B is the hypotenuse. 600 is opposite that, opposite the angle we know, okay? So the sine of 15 degrees equals the opposite over the hypotenuse. And if we solve this, we multiply by the magnitude of B, doing a little bit of algebra here, and then we'll have to divide by the sine of 15, so we'll have 600 over the sine of 15 degrees, and we get the magnitude of B, which is the weight of the boat and trailer, to equal 2,318 pounds. I'm just going to round that to the nearest integer for right now. Okay? So the boat and trailer combined weigh 2,318 pounds. Now, we have two more examples, and these two examples are going to show us really how valuable it is to be able to write these angles in a standard, in component form. All right, the angles in standard position and getting the vectors in component form. All right, so here we have an airplane that's traveling at a speed of 500 miles per hour with at a bearing of 330 degrees, okay? Now I've drawn this right here, and you'll notice I've already labeled this 120 degrees. And the reason is because if this is 330 as a bearing, bearings are measured from due north clockwise. Angles in standard position, direction angles for a vector, are measured standard position, okay? From due east, we could say, counterclockwise. All right, so we had to do some figuring out here of what angle that was. And we can see it's 120, but notice how we get that. This 330 is 30 degrees short of a full 360. So this angle right here is 30. Well, we know this is 90, and that's how we get 30 plus 90 equals the 120 for the direction angle of our airplane. Okay? We also can say that the magnitude of this airplane's vector is 500 because it's 500 miles per hour. That's our magnitude. All right? So as a result, we can give vector 1, the airplane's vector, as 500 times the cosine of 120 sine of 120. Okay? We would simplify this a little bit. It's 500 cosine of 120, that's a 60-degree reference angle, so that's a negative 1/2. And sine of 120 is a positive root 3 over 2. Okay? So we would then get a vector of negative 250 root 3. Okay? So that is vector 1, that is our airplane's vector. Okay? Now it says the wind, as the airplane reaches a certain point, it encounters a wind blowing with a velocity of 70 miles an hour in the direction of north 45 degrees east. So again, we're given a bearing north 45 degrees towards the east. Okay? Remember, you start at north. Here's east, so you're rotating towards the east 45 degrees. Now, the angle in standard position is going to be 45, but it's 45 because to rotate from the positive x-axis to where our vector is going to be 45 degrees. So that's our direction angle, and then also we are told that the velocity of that is 70 miles an hour. So 70 miles per hour. All right, so our wind, which is vector 2, is 70 times the cosine of 45 sine of 45. Okay, now sine and cosine are both root 2 over 2. So if we multiply the 70 in, it's going to be 35 root 2, 35 root 2. That's our vector 2. Now, this asks us for the resultant speed and direction of the airplane. Now, here's a little tip. Anytime you hear this word resultant, you should think vector addition. Vector addition. Okay? Well, the two vectors we're adding together here, as you can see in our diagram, are the airplane's vector and the wind's vector. The wind, notice, is blowing the airplane off the course it's trying to fly. It's off of that 120 degrees a little bit because the wind's blowing it off course. And this vector v is what the airplane is actually going to do. So, we have vector addition. We do v1 plus v2. V1 is negative 250, 250 root 3. V2 is 35 root 2, 35 root 2. Okay? We add those together. And we could even do this as a decimal. We have a negative 250 plus 35 root 2, which is a negative 200.50. And then we do 250 root 3 plus 35 root 2, which is 482.51. All right? So, there is the resultant vector. That's what's happening right here. Okay? So this is telling us what the plane actually does. So we need to now find the magnitude of this to get the resulting speed. So that's going to be the square root of negative 200.5 squared plus 482.51 squared, which is 522.51. And this would be miles per hour, because this is the magnitude of the velocity, which is our speed. Okay, so you notice actually the wind, even though it was pushing us off course, it was actually pushing us so that we were going a little bit faster than what the plane could do by itself, because it was just trying to go 500. Okay, so finally we need the direction. All right, the direction angle. If you remember, the direction angle is theta, so tangent of theta is b over a. So 482.51 over negative 200.5. That gives us, if we take the inverse tangent, theta equals negative 67.4. So here's where we have to think. We have to look and see, all right, our horizontal component is negative, our vertical is positive. We can see here that's the case. So we're in the second quadrant. All right, tangent is negative in the fourth and second quadrant, and this angle right here would actually be in the fourth quadrant. Okay, so this is going the wrong way, but it does show us our reference angle is 67.4 degrees. So that means in the second quadrant, this angle would be 67.4 degrees. So that means 180 minus that would be 112.6 degrees. That's going to be our angle theta, 112.6 degrees. So that's the direction the plane will go. Notice it's about 7.4 degrees off the where we were trying to aim at 120, and this is the resulting speed. Alright, finally we have a resultant force that we're trying to get, and we need to figure out the angle that we need to pull with the second force in order to get the resulting force that we want. Alright, so this one takes a little bit of thought here, but let's stay with me and we can figure this out. Alright, so here's the case. We have force 1. It doesn't give us a direction for that one, so I'm just going to put that on the x-axis. Alright, and that's 45 pounds of force. Okay? Force 2 is 60 pounds. However, it doesn't tell us what angle force 2 is at. I know this is 60, and I'm doing vector addition. Alright? I should make it proportional. If that's 45, then 60 should be about a third again as long. So that's 60 pounds of force. Okay? And I know my end result is going to be 90 pounds of force. Okay? Now, let's think about how we would do this. Alright? This is going to be theta. And we need to do some vector addition. We're going to do it with component vectors. The nice thing is, because I drew the first force vector the way I did, this is just the vector 45, 0. Okay? We're not going up or down, we're just going 45 to the right. Okay? Now 60, we're going to have to use our formula for. So it's going to be 60 times the cosine of theta times the sine of theta. Okay? Now, that's going to be 60 cosine theta, 60 sine theta. Now, the resultant force, notice this is the magnitude of the resultant force. Okay? Well, first of all, I need to get what that actual force vector is. Alright? I'm going to call that vector F for force. Okay? That is the sum of these two. So it's going to be 45 plus 60 cosine theta and 0 plus 60 sine of theta. I'd say, okay, well, how does this help us? Well, we know that the magnitude of this force vector has to equal 90. Okay? So, how do we find magnitude? Well, we take the square root of the horizontal component squared, 45 plus cosine, oh, not just cosine, a 60 cosine, theta, and that's squared, plus 60 sine theta squared, and this has to equal 90. Okay, so we've got a little bit of work to do algebraically here. 90 equals, actually, you know what, first of all, I'm going to just square both sides to get rid of the square root. So this is going to be 8100 equals what's in the radical, okay? Now, what's in the radical needs to be squared, so I'm going to FOIL first of all. I have 45 squared, which is 2025. plus 45 times 60 cosine plus another 45 plus 60 cosine. So that's going to be 45 times 60 is actually 270, or I should say 2700, and we're going to have two of those. So that's going to be 5400 cosine theta plus 60 cosine being squared is going to be 3600 cosine squared theta. And then I need to square the 60 sine of theta, so that's a 3600 sine squared theta. Alright? Now this looks harder than it's going to be to solve, alright? First I'm going to subtract this 2025 from the 8100, so that's going to be 6075. I have a 5400 cosine theta. And then notice here I have a 3600 cosine squared plus a 3600 sine squared. Well, that's 3600 times cosine squared plus sine squared. And what do you know? This is one of our identities, Pythagorean identity, that equals 1. So this is just a 3600. I'm going to subtract that to the other side. So I have 5400 cosine of theta is 6075 minus 3600. So that's going to be 2325. Or I should say 2475. And when I divide it by 5400, I get 0.4583333 equals cosine of theta. Okay? So I'm going to take the inverse cosine of both sides, and I get 62.7 degrees. Okay? Now this is what's interesting here. Okay? It doesn't say anything about what theta has to be. So yes, theta could be 62.7, but notice cosine is also positive in the fourth quadrant. Okay? 360 minus this is going to be 297.3 degrees. And if you notice here, if I were just to draw this down this way, okay, so at a 297.3 degree angle, I would have the same resultant vector just at a different angle. Didn't care what the angle was, we just cared that it was 90 pounds. So there actually are two potential outcomes for this one that would give a resultant force of 90 pounds. Okay? So we have a number of different applications of these unit vectors. All of these are going to be easier to handle pretty much using the unit vector than they will trying to draw the whole thing out and use the law of sines or the law of cosines. That can be done. If you want to explore and try it out for yourself, you're welcome to do that. But a lot of these are going to be a lot easier if you use the unit vectors in the component vector form. Okay? So now you have a little bit of practice you can try, and we can take questions later.